So what I've been doing recently is using this thin bin, zooming on this and seeing all this wealth of colors and being like, let's try to take this bin, just fiber stuff, and then let's try to isolate agglomerates in the orientation space, or clusters in the orientation space. And if you have a lot of solutions that happen to end up in the same orientational region, they are probably associated to an actual fiber in that voxel. So then you can cluster them, get a certain fiber, and compute statistics in there to be able to characterize this specific fiber and the other ones along them. Doesn't matter. So that's the key thing. Automatically bin these solutions in their orientation subspace. I call it subspace because it's a smaller space than the total one. And use clustering. So just going quick on this, this is a paper that is almost done to be submitted. It's been done with people in Cardiff, Chantal Tax and Derek Jones, and Philip Schmankiewicz has also helped a lot. I don't remember his affiliation here, but maybe Harvard and Lund. I don't remember. So I did do some clustering approach. I will skim very fast through it, but this is all these points that you see here are points that are put it as a thin bin solution by one of the bootstrap realization of the Monte-Carlo inversion. It doesn't matter which bootstrap, I just put them on the sphere and I cluster them there. That's the key thing. And to do this, I've been using what's called the density peak clustering algorithm that I kind of modified. As a distance, it doesn't appear from this equation, but the distance is actually simply the shortest angle between 2 points. So between point I and J, I take the shortest angle. So that's a proper measure of distance on the sphere. And to cluster them, you're going to use some density measure, doesn't matter. You're going to use some delta distance that tells you the minimal distance between two distinct points so that the point J has a higher density than I. So if you want a cluster, the centroid, the center of that cluster, should have a high density, should be surrounded by a lot of points, makes sense. And it should have a high delta distance. It should be far from the closest points with a higher density than his, right? So that's the criteria used for clustering this set. And then I implemented a few things to make it automatic and robust. Doesn't really matter. I'll just skip past this. And then you get this, so just going through again, you have these Monte-Carlo realizations with different thin bin solution. All the rest has been taken out, doesn't matter. I do this clustering on all of them at once, doesn't matter which realization they come from. Then I go back to this solution. I'm like, well, actually, this one was that dot in the blue cluster. These two were 2 dots in the red cluster. And for example, this one was one of the outliers that was detected by the clustering approach, so I won't count it. And then for each of these bootstrap realization, you're going to compute statistics for the measures for the blue, green, and red clusters by averaging solution belonging to the same cluster. So for each of these bootstrap, you get 1 diiso for the blue cluster, 1 diiso for the red cluster, 1 diiso for the green, 1 orientation, 1 d delta, 1 T2, whatever you have, 1 by cluster, 1 of each of these set per bootstrap, and then you can compute statistics along this bootstrap for each of these clusters separately. What you get, and this is in the orientation averaged space, you get these clusters that are a bit more refined because the orientation of the points have been averaged within each bootstrap. So this gives you a pretty good measure of peak orientation, and you can even define a cone that makes sense and that may be different for different fibers. So this is kind of original compared to anything that has been done in tractography, that you can get these cones different for different fibers. Then implementing it in the natural algorithm is a bit harder, but this is different. And for example, using this clustering, you can get all of these peak orientations that I draw here. This looks a lot like any peak map you would get from any other technique. The only difference is that here, this has been obtained without constraints. And this is the key thing, because that makes it reliable in non-healthy brains. It's the same for the ODFs that we showed before from the Monte-Carlo inversion. That makes them robust. And that's the main difference compared to modeling, for example. Here is a figure that I already showed a lot of you, I guess. where I isolate one crossing, that is the one I showed you before, between 3 fibers. And using this clustering, I can not only get the median of these, for example, d iso, d delta squared, T2 and R2 along different fibers, I also estimate the error bar on this to some extent. So this is the interquartile range, and this is the median point. And then you can use statistical testing to assess whether or not two fibers are very distinctively different. And in that case, you can see that the T2 here is much larger. Well, it seems much larger in the corticospinal tract, the blue one, compared to the other ones, which we saw already before in multiple papers. So I can test that. Statistically, it makes sense. They are different. But also, you can also try to track it without tractography, because I haven't implemented this yet. But you can at least look at the peak map that I showed you before, but colored with the median T2 along each of these clusters. And you can see that the corticospinal tract here in this coronal map is bright red compared to the other ones. Makes sense. And this happens along the entire tract. And here you have also a part of the posterior, the back of the corpus callosum, that is called the forceps major, because it's bigger than the forceps minor that is in front here. And this also has a very bright red T2. So it seems like he has a higher T2. And these two tracks are different from other tracks because of some, for example, it could be the high myelin content, the fact that they are very large axons apparently compared to other bundles. Maybe or maybe not, that explains this T2, I don't know. I just know that they are at least they are different from other bundles by a few respects. So that's one thing to consider. But at least we are sensitive to it and we can see it. It's kind of cool. I also try to track it in the entire brain by taking this median T2, taking the maximum within a voxel of the median T2 for all clusters, and then taking the max across a certain direction. So this is called a maximum intensity projection map. It doesn't matter, but the thing that it gives you is that if you look at the corticospinal tract, which is the white arrows, this is a sagittal slice with this is the front and this is the back of the brain. And the forceps major is in purple arrow. You can see that consistently throughout the brain, that's the point of these maps, they have a higher T2. So just multiple ways of seeing the same information at different levels. So just to finish, this kind of clustering algorithm, it has potential to just remain very local if you want. So it can be very local to assess fiber-specific microstructure, and you have a lot of very local diseases that can happen. For example, multiple sclerosis or traumatic brain injuries that you may want to track locally along a certain tract. So that's something that can be done using this, definitely. You just have to implement it. It has potential in tractography. You have these peaks for each cluster. You have these uncertainty cones that can be defined for each fiber separately. That is very interesting. It's free of partial volume effects to some extent. We have to check how much it is, but I am pretty sure it's more free than any other model by design. So obviously for surgical planning, like tracking around a tumor, we have edema, this is definitely something you want to try out and see if it improves anything, because this has a huge impact for people with actual brain tumors. Also, this kind of clustering can accommodate with non-orientational information, which is literally the main problem with tractography as of now, to just rely on orientation. So then if you know that, for example, the CST has a higher T2, maybe you can use it to just track the CST, knowing that it has a larger T2, and avoid going out to other things that don't make sense, to other bundles that don't have the same T2. Finally, in tractometry, which is a measure of stuff along tracks, measure metrics, you can track either changes in along certain tracks if you have your development of the brain, aging of the brain, or if you're under treatment and you want to check if it's actually solving something along a affected tract. That can be something. Also, you could try to compare different groups, see if different groups have various different bundles, maybe because they have a different disease or something like this, or different stage of the disease. That can be done, because that's something that is already heavily done in the tractography field, but we can add our grain of salt to it. And for the future, we need to optimize the acquisition scheme for the Monte-Carlo inversion. This is essential. I cannot stress that enough. Comparison of tracking strategies going deterministic, probabilistic, using peaks or DFs or something, peaks and cones and stuff. This remains to be done and implemented. Also, using T1 and T2 to help the tractography, it implies that you have to extend what's called the tracking stepper. The tracking stepper is the thing that gives you how to project the fiber from one voxel to another and continue your tracking process by step. So that's why it's called a tracking stepper. And it needs to include this relaxation metrics if you want to help the tractography. And finally, you could use the clustering maybe as an input for commit, which is, I don't remember the acronym per se, but it is one framework that will take some model or some compartmental model as prior information. Actually, our clusters could be kind of redefined as being compartments in this kind of model some way. It is straightforward. There are many ways of doing it, but straightforward, each of them. And then you use that as prior information to take tractograms that have been obtained by whoever wants it, wherever in the world, doesn't matter, and to see if we can filter out tracks that don't explain the information obtained by this compartmental model. In that case, would be the clustering. So thanks for your attention. Sorry for the kind of longish presentation. It was a mouthful, but I do hope that you got something cool out of it. Thanks again.